So I want to make a correction from yesterday's notes. That correction is very minor. Okay. Yesterday I said the anode was positive and the cathode was negative. That is incorrect. Here's why. All right, I got mixed up. Anode, right? It gives away electrons, which are negative. So coming out of this anode side is negative items. Anode is the negative terminal. Cathode, it is positive. Okay, think of this. Opposites do what? Attract. Opposites attract. So the only way for those electrons to follow this path is for that cathode to be positive and attract those electrons coming out of the anode. All right, I just wanted to clarify that so everybody is up to speed on that. Okay, questions? This is the only part we needed to correct from yesterday. Let's go ahead and get started with our second reaction, our second example problem. So yesterday we started off and we said, all right, hey, here's an equation. Tell me what the standard cell potential is. Now, I give you two equations. Both of these things are written right now as a reduction reaction. For a chemical cell to happen, they both can't be reduction. One has to be oxidation, one has to be reduction. So the first place that we start is this. We start out and I am going to look at this. On my chart, I'm going to look up I2 plus 2 electrons goes to 2I minus. And when I look that up, I find that I have a value, a cell potential for this to be a positive 0.5355 volts. Okay. Then I do the same thing for iron. Now, just like copper, iron has or multiple oxidation states, multiple positive charges there. So make sure you get the Fe plus 2 electrons. In this segment here, the cell potential that is listed on our chart is negative 0.447 volts. Okay? Now, what we can do and just ask ourselves is this. We ask ourselves, of these two numbers, which is the most positive?
0.5355 volts.
Yeah, so it says positive 1, and the other is negative. So right here, this equation that I have in green, the most positive is our reduction reaction. Okay, check. If this is reduction, what can we say about the Fe2 plus reaction?
Oxidation.
Very good. All right. So now that sets us up to be able to easily calculate what is our standard cell potential. So if you remember from yesterday, we said E cell, the standard cell potential, is our cell potential of our reduction reaction minus the cell potential of our oxidation reaction. So we just plug these numbers in just as we see them above, and we are going to start out with that positive 0.5335 volts. Now we say minus, and because our oxidation is negative, I always like to put it in parentheses, negative 0.447 volts. And we turn to our calculators. Yes?
Yeah, put the right number.
I've done that twice today. Good catch. I know. All right, so now we go through this. Again, be careful of signs. So we have a positive 0.5355 minus a negative 0.447. and we get a value, our E cell, which I'm just going to write to the right here, of positive 0.9825 volts. Okay. Now we do this part that we did not talk about yesterday, which is cell notation. It's not hard. We just have to think about the things that are involved here. So our cell notation is essentially taking those beakers that we wrote up, and we took the time to take 5-6 minutes to actually go through and label that, and we're going to identify it in a very simplified manner. Okay. The first thing that we have to do is we have to take this oxidation reaction, and we have to actually make it an oxidation reaction. It's written right now as a reduction. Very simple. What do you think we do to make it written as an oxidation? Well, flip it. So what we're going to do, you guys are on the right track, is this. This right now is written as a reduction. So we flip-flop our products and reactants, and so the oxidation equations would look like this that I'm writing in our equation. Okay? Now, how we start writing our cell notation is this. We look and we say, all right, we're going to start with Fe as a solid, and we're going to put that right here, Fe as a solid. Then we draw one line to show, hey, this is what is happening in the oxidation, and then we write what's on that product side of that flip-flop equation. Now we write Fe2 plus, and a lot of times they don't even go to the extent to write down AQ versus solid. They just put Fe and Fe2 plus. That is the oxidation half reaction. These things are separated by a double vertical line, and that represents two things. One, we're switching gears to our half cells, and two, it represents that the cells are connected by also two things, a salt bridge and a wire, just like we showed in the big overall picture. And so now on the other side, we start with this. We start with our I2, and I'm going to put solid because I like to represent the state of matter. A single line, and then we put 2I minus, and that's all we would do. That would be our cell notation that we have. So very simply, very quickly as well, it represents everything that we wrote down in that particular beaker we identified yesterday on that picture. Okay? That is our simplified way to show our particular reaction. Okay? Questions? Yes?
So the stuff from yesterday is just everything before the cell notation,
Yeah.
Okay.
Yeah. I'll have a video of that too. I didn't quite get to it yesterday. All right. Any other questions? Does anybody still need this? Okay, moving on here. We have our next type of example. The biggest thing, yeah, you have the steps, but to be a natural or a spontaneous reaction, that overall equation, when we do reduction minus oxidation, has to be positive. That is the key point there. A positive voltage means a spontaneous reaction, means things will naturally happen in our voltaic cell. So here we go with another example. Oh, look, cell notation. You can see here that we have no states of matter. All right, so they simplify it here. I start out and I look at this. It says use the standard reduction potentials to calculate the overall cell potential. And so I am going to start with this. On the left-hand side, what did we just say? What type of reaction was this? Is this the reduction or the oxidation reaction?
What?
I heard it somewhere. Someone said it. Oxidation. Left-hand side in this notation is our oxidation. Now, since we're already here, I'm going to look up the cell potential of this half. So we take a look. The only thing you have to be aware of, remember, reduction potential, this is oxidation. So technically, you're going to look for Li plus. And so Li plus is actually the first thing. What's that? Yep.
0.0404.
Very good. Oh, I didn't write the 0. 0.401, correct? All right. Then we do the same thing for our silver. Silver, if this side over here on the left is oxidized, then silver is, yep. So reduction here is what I just circled in pink. And so we do the same thing. We say, all right, we find Ag plus going to solid Ag. And
0.7996.
996, right? Volts. All right. Now, all we have to do is this. I'm going to write the equation. You don't necessarily need to write this again. But our cell potential is always going to be our reduction potential minus our oxidation potential. Okay, from there, we just start plugging numbers in. And so we'll have this. Our cell potential is going to be equal to the positive 0.7996 volts minus our negative 3.0401 volts. Put the parentheses here, turn to our calculators. Again, like you said, minus a negative is just really adding. So when I do this, I get a total value, a standard cell potential of 3.8397 volts. And I should add one more thing. I always like to put the sign just so we know, okay? Just so we know that we have that there. Questions?
Mr. Reeves is out there. Can I go talk to him?
No.
Yeah, he said really nice guy. Why didn't he?
He's a nice guy.
Yeah, that's right.
Okay. Anybody need this?
He does have a rig.
One more problem. Hang in there, and then we can
One
look
more.
up the window.
Holy cow! Bryson told me to ask me if I should go over to the door first.
No. So now we get to another type of problem. Almost a start that we had previously. So what we're going to do is this. Just like we did on the very first example problem of this section, I'm going to start out, I'm going to pick one reactant, in this case 10 or SN. And I'm going to say 10 as a solid. I draw my arrow. What of my products? Very good. That's the most similar. Now we have to balance out the charge.
It's got a 2+, so we need 2 electrons.
There we go. All right. We need 2 electrons on the right because we got to balance out the charges. Charge of the left side is 0, so we add 2 electrons. That's done for right now. Now we move on. We move on to our 2 Cu, 2 or just 1+. That's very important. Just 1+.
Leave the space.
There we go. And then we go to solid copper.
Can you not put it in front?
You can put it in front. Yes, you can. Yes. The reason I write it like that is because I'm used to on my chart having the electron written second. But it is not wrong to write it out in front.
Okay.
Good question. So how many electrons here?
2.
Okay.
We
Again,
got 1, right?
no, that's a really good point. This is already, if we read this, this is a balanced redox reaction. I know that was kind of the difficult part, but a balanced redox reaction will have the same electrons on the left and right hand sides when we write it like that. That's why it's balanced. So that's a really good point. Now we need to figure out oxidation reaction versus reduction. So let's look at the green equation. Green equation here, Sn charge is 0. Goes to a charge of 2+. It gets more positive, which means it lost electrons to get more positive. What process is associated with losing? Oxidation. Oxidation is loss of electrons, oil. So right here, I'm going to say this is an oxidized. And then, again, use common sense. That means the pink equation is what? Very good. Then we need to do this. Oxidized equation. Remember, it would actually be flip-flop in our chart. If we look up our oxidized reaction in our chart that I handed out yesterday, you're going to look for, okay, Sn2+, let me get the right color, go.
-5.3.
That's
Nope.
so wrong.
Yeah, it's very
Negative 0.1375.
1375.
Yeah.
Okay. So check. Now, I did not realize until I did this problem first period that this chart, there's actually a more inclusive chart, so it's a little bit bigger, that this chart did not include this copper with a 1+. Copper is listed multiple times on your chart. There's even additional coppers that we have. And so I had to turn to my other chart here. But if I find copper with a +1 charge, +1 electron goes to copper. And notice I said ones on all of those. In this process, coefficients does not affect your cell potential. So I could have a coefficient of 30 or 40. It's still going to give me the same number out of here. Okay. So if I look this up, or if I actually gave you the right chart, you would find out that this has a value of positive 0.521 volts. Okay. Now, all we have to do is plug it into our equation. So our cell potential, what's the first thing we list in our formula? Reduction, right? So the pink equation, I turn to positive 0.521 volts minus my oxidation, which is negative 0.1375 volts. And again, we turn to our calculators. 0.521 minus a negative 0.1375. I press enter, and my cell potential is this. My cell potential turns out to be a positive 0.6585 volts. And now, real important, a positive cell potential means what type of reaction? You got spontaneous or non-spontaneous? Spontaneous. It's going to happen. If it's negative, non-spontaneous, but positive, so this is spontaneous. Okay, so you can see from this equation, cell potential reduction minus your oxidation, we can do several problems. This is the base for your, I'll call them quote unquote difficult math problems. Okay. Questions?
Nope.